Okay, we're going to talk about how the tunnel diode operates. So we're going to start by looking at it on the forward bias. This is the N side, this is the P side. Right now we're at equilibrium, so the Fermi level is continuous through this PN junction. And if we look at the IV curve, we're right at the origin, so no applied forward bias voltage, no current through the tunnel diode. Okay, so put a small forward bias across this PN junction. So forward bias, my band's offset in this direction by the value of the forward bias voltage. Okay, and still in this diagram, these gray shaded areas represent filled states. This white area represents empty states. Okay, so I have some filled states in my conduction band at these energy levels. I have some empty states or holes in my empty states in my valence band. And so the electron has a possibility of tunneling through from this energy level to these energy levels because there's states that it can fill in the valence band. And because each side of this junction is degenerately doped, this width of the depletion region is very, very small. It doesn't take that many, or not that many charge carriers have to, the depth of the depletion region on either side of junction is not that deep because there's such a high concentration of charge carriers that in order to form that depletion region, I don't have to go far onto either side of the junction. Okay, so I have a very narrow width to this potential barrier here. I have some electrons here. I have some states that they can go to here. So that's a good condition for tunneling to occur. Okay, so the electrons in these conduction band states tunnel over into the empty valence band states. And once the electrons start tunneling over, then my current will, that still corresponds to current increasing as I increase the forward bias. So from equilibrium, we went up to this curve. We have an increase. Now we're going to add a small forward bias. So what that does is it offsets the Fermi levels by an amount equal to the forward bias voltage. So what that also does is it makes some electrons in the conduction band, represented by these filled states in the conduction band here. They are now at the same energy as some empty states in the valence band here. And the distance of separation between this electrons in the conduction band and these empty states in the valence band is not very large because of the depletion region being very narrow in the tunnel diode because both sides are very highly doped. Okay, so this width of this potential barrier is small. That means that there's a possibility that electrons can tunnel through that potential barrier, and electrons in the conduction band will tunnel through and end up in the valence band. So this movement of electrons corresponds to a current through this PN junction, and thus you'll get an increase in current on the IV curve as we start to forward bias the tunnel diode. If you increase the forward bias some more, there's going to be more states in the conduction band that line up with empty states in the valence band. So more tunneling can occur, and the current increases a little bit more. Right at this point, this is going to be the point at which you get the maximum amount of current through the tunnel diode, because all of my energy levels in my conduction band line up with empty states in the valence band. So this is the maximum flux of electrons that I can have tunneling through the tunneling from the conduction band to the valence band. Okay, so I've reached a maximum current through the tunnel diode. Now, if I keep on increasing forward bias, what do you think will happen?
It's just going to saturate, create trap states. Oh no, decrease?
Okay, so, well, I guess there's three possibilities, right? Either the current stays the same, current goes down, or the current goes up. So what do we think it is? When I increase forward bias past this, how are the bands going to shift?
EFP will continue to go up, EFN will continue to go down, and then
Yeah, maybe I need to label this. This is EFN.
oh yeah, the other.
This is
the other
EFP.
way around. So EFN goes up, EFP goes down.
Okay, so EFN is going to still go up relative to EFP, because this is that's my forward bias. Now, as we keep on increasing the forward bias, eventually we get to this point where all the filled states in the conduction band are opposite of empty states in the valence band, and now we can have the maximum flux of electrons possible tunneling through from the conduction band to the valence band and producing the most current through the tunnel diode. Okay, so we're at the maximum current point in our operation of the tunnel diode. Let's go to the next one. So EFN versus EFP. So this is a larger forward bias now. EFN shifted up more relative to EFP. But the position of EFN relative to the conduction band energy, this doesn't change, right? This gap is not affected by the forward bias voltage. Okay, so that means my conduction band edge is also shifted up relative to EFP. So now, if I want to stay at the same energy level and do tunneling, I have less electrons available, or less total electrons available to do the tunneling, because these electrons up here are already at a higher energy level. So if I want to tunnel over from one energy level, keep at the same energy level, I have less total electrons available. So the current is going to go down, and that's where you start. We were at this point here, this maximum in the previous case, but now we have less electrons available to tunnel, so the current starts to go down. Okay, and now the current is going. As we keep on increasing the forward bias, the number of electrons that are across of empty valence band states start to decrease, because this distance between the Fermi level on the n-type side and the conduction band energy, that stays fixed as a function of forward bias, even as this offset, which is equal to the forward bias voltage, keeps on increasing. Okay, so for example, in this case, I have electrons in these energy states, or this energy level and below. That's directly across of empty energy states in the valence band, but there's not as many electrons there as on the previous slide or in the previous case. So the flux of electrons from the n-type side to the p-type side is decreasing, and so you can see our current is decreasing from that maximum that we had before. And this is important because now if you take a tangent to this IV curve, then this slope will now give you a negative resistance. If we keep on increasing the forward bias, eventually, the bottom of the conduction band will be above the top of the valence band, so there's no empty states across of the conduction band energy levels for the electrons to fill, and so there's no tunneling occurring anymore in this case. Instead, the only way for electrons to move from the n-type side to the p-type side is for them to go up this potential barrier in the conduction band. So this is the same case as we have for a standard forward biased p-n junction, and that's why you can see that as we look at that IV curve, if this dashed line represents the ideal diode current equation, now this tunnel diode starts to follow that ideal diode current equation, under forward bias. Another question is, what about reverse bias? Okay, so if we reverse bias the tunnel diode, we're going to offset the Fermi levels on either side by amount equal to the reverse bias voltage. Now you can see that when we do that, these gray states in the valence band represent filled states in the valence band. So I can have electrons from the valence band tunnel through the potential barrier and end up in the conduction band on the n-type side, because above the Fermi level on the n-type side there are going to be empty states. Okay, so as you reverse bias the tunnel diode, there's as soon as you start reverse biasing it, there's going to be electrons in the valence band that can tunnel through to the conduction band. So as soon as you start reverse biasing the tunnel diode, there's going to be electron flux and therefore current through the tunnel diode. And so you can see that all the reverse bias voltages on this IV curve are negative. So as soon as we start making the applied voltage go negative, which corresponds to reverse bias, you start to get an increase in current through the tunnel diode. So this is reverse bias. So unlike a standard p-n junction, the tunnel diode is not good at blocking current from going in this direction, under reverse bias. That's not what you want to use it for. You want to use it for the fact that the IV curve has a negative slope in this region of operation.